Hi, I'm Ruben, and today I'm going to talk to you about Hydra. Hydra is the system that Conduction uses to do agentic development, and it is how we turn vibe coding into variable and safe coding. So we will be touching on several subjects. We'll be talking about the history of vibe coding, how we're going to harness the power of vibe coding, how we use skills and specifications to do that, how we created the Hydra ecosystem, and how we actually managed to run this pipeline completely automatically. Now, vibe coding in itself, of course, has been a relatively new concept. It's been around since early 2025, and it basically describes developer vibing. So he's talking to the AI, asking questions, looking at what it does to the code, looking at the application, and then making changes. And it's generally used to develop from a front-end only perspective. So the developer doesn't normally look to the backend, doesn't look at the actual code. He's just vibing along and creating an application. And this, of course, has revolutionized coding in the sense that it goes very much faster and it has broken up coding to the democratic ecosystem. Everybody can code these days. It also introduced a lot of dangers over the years, and we've been trying to deal with that for some time. At this specific moment in time, and we're talking the summer of 26 here, around 64% of all code is written by AI. Over 92% of all developers use AI in their daily operations and work, and it has a market size of close to $5 billion. So that's a tremendous amount of work. So if we look into the future, then we'll see that early next year, around 60% of all code will be made by AI. That means over half the code. So that's a certain tipping point which we then pass. We'll also see that there's a fast explosion of repositories. So that doesn't mean that not only is the market size actually growing, there's also more apps, there's more software out there, there's more choices. It does, of course, come at a cost. And vibe coding has a tremendously bad reputation for security. And actually, that's rather well deserved. So almost half of all AI-generated code ships with vulnerabilities. Very few developers rightfully trust the output of vibe coding. We are also seeing that there are specific attack patterns emerging. So we now have packages that insert worms, and they are inserted with package management. Axios actually got hit with this. Now, just for your mind space, Axios has over 100 million downloads a week. It's one of the most used libraries in the world. They had an upstream attack, so that means that one of the packages that they trusted got a Trojan in it, and then that got into Axios. They did fix that within 3 hours, but they already had a couple of million downloads in those 3 hours because it was during working hours in America. So this propagation of worms goes very, very, very fast. And it isn't even the worst of it. The worst of it is that AI code has the tendency to hallucinate. And it tries to invent packages that aren't there, and those packages occasionally do end up in the package list of applications, meaning that every time the application is booted, then those packages are trying to get downloaded. Now, the only thing you have to do right now is you go on GitHub and you see who is using a package that isn't actually there. Then you register the package and it gets automatically downloaded into the software. That happens a lot. The real blatant thing, AI, like humans, tends to make mistakes. So you can't blindly trust AI to always deal with the most proper code in the most proper way, or to write the best code, or actually not to just introduce bugs as it goes along. What we need to do is we need to harness the power of AI. Of course, been doing that for some time. So the first thing that we did is we did prompt engineering. Okay, so how am I gonna ask my question and how am I gonna steer AI into making the right choices and the right results? We ended up with very long prompts and prompts were actually shared on GitHub and that became a whole science of its own. Then we came up with, okay, we need to give AI a memory. So we introduced reg, function calling, and we gave AI a tool set to work with. Next thing that we ended up with is, okay, we're going to do autonomous agents. So we're going to run either sub agents or we're going to cron agents, but we're going to do stuff that makes agents work on themselves, have these tools, and continue working on prompts. And then that got further stabilized and said, okay, actually I want to define how an agent behaves. So we're going to do context engineering and we're going to do skill engineering. And a skill, of course, is nothing more or less than a markdown file that the agent reads and uses. Now, the last iteration of that is, okay, so what if we pick up all this knowledge and we go back into time and we're looking at how we did stuff before AI happens? And what if we do stuff like Moscow and order systems and apply them to skills? And then the concept is, okay, so we need to then specify what we want to get. So we're going to end up with spec-driven manifests. And spec-driven, of course, is very much like we used to do stuff. So you can compare that to a very complicated and structured way of writing issues. Let's take a small look at what a skill actually is. A skill lives in a skill set being a folder directory somewhere in your computer that contains MD files, and those MD files then tell the agent how to behave. So that's basically a set of actions or rules that an agent needs to follow when doing a certain action. And that gives the feeling that the agent has a skill. Of course, skills are a very human name. It's more of a process that needs to be followed. In the Hydra context, then we always start with a spec. And a spec is derived from open specification. And it does a couple of things. First of all, it Moscow's our requirement. So we want to build this functionality, then the system must do that. We want to have this result, and that makes it viable. Then we're going to split that into three separate MD files. First of all, we're going to do a proposal, and the proposal tells the agent what we want to build, and most importantly, why we want to build it. So what's the expectation? Then the design tells it how to technically build that. So you need to build those methods or those functions or connect to that database or use this sort, etc. And a task list is nothing else than a markdown task list where we can follow, okay, these are the tasks that need to be done to build this specification, so to provide this functionality. A specification is also always a functionality. And then the agent can actually check stuff off of the task list, and then we know how far it is, and then we can, of course, divide it among multiple agents working in multiple turns. An obvious gap, and that's architecture. So specs are always focused on features, but of course you have how your application works, and you've got all of these stuff in place that has to be in each feature, or that each feature needs to adhere to. For that, we use architectural design rules, or ADRs, and ADRs are also markdown files which can be read by agents, but should also always be gated, and we'll get back to that later. But keep in mind, specs describe a functionality, ADRs describe the application as a whole. So then how do we get to fully automated development? Well, first of all, we set the human in the loop, so that's the center of the entire process. Now, this human, be it more of an artistic developer, then starts with writing specs. Then those specs get fed to a builder that picks up the specs and builds them. Then a second agent with a different skill set takes over and does a code review, and if any adjustment needs to be made, makes adjustments. Then another agent does a security review, and if any adjustments need to be made, makes the adjustments. And then in the end, it gets to a validator, and the validator never does adjustments. It's just there to validate. It then takes up the same skills actually as the code reviewer and security, reviews everything again. Then it also runs all the checks again. And then if everything figures out and it's all right, and the code validates, and the front end actually validates against the specifications written, it's handed back to the developer, and the developer can decide to merge the code. Or if on any of these stages something is wrong, then we go back to the builder and we do another loop. And we do this loop max 3 times, because when we've done it more than 3 times, then we think, okay, something apparently is wrong, so we need to go back to the drawing board, or back to the specs in this case. Now that means that there's always a human in the loop. The question is just, where do you put your human in the loop? And we put them front and back. Now, look. So the moment that the builder picks up any issue, we automatically starts a draft pull request. And then any agent that does anything actually notes that down on the pull request. That means that we can always read the pull request to see exactly how the code that we're reviewing before merging has been established. That means that the entire pipeline is also always driven by labels. So anytime any agent touches the issue or the pull request, then the issue or the pull request get labeled, and then we know what's going on with the issue and the pull request. And that means that we can watch what our agents are doing. And that gives us a live dashboard. So we can just use the normal dashboard, normal projects that are in GitHub to see how our issues are moving along the dashboard and which agents are actually doing something. So then comes the question, how do we trust the output of this agentic process? Well, first of all, we don't. That's why there's a human in the loop. The human in the loop checks the code. Then second of all, we don't. We use mechanical gates. So we say code quality and coding standards get tested by mechanical gates. And then we also do end-to-end testing with Playwright. We use Newman to test the API endpoints. We use unit tests. So we use a lot of tooling. And then we also say every architectural design rule that we have needs to be gated. So if you have an architectural design rule, then that also needs to come with mechanical test. 12 tools. We have 22 gates because we have 22 ADRs, and we have zero tolerance. So anything that is a warning or higher means that the code gets thrown back into the builder, and that first needs to be fixed. So for each line of code, we want to know what happens. Now, of course, we have our commit history and our change logs, and each agent operates on its own Git account. But we also introduced a tag system of specification. That means that anytime a method or a function gets altered, then a specification tag is added to that function that then refers the specification that was used for each function. So if we're looking at code, then we also always have the context in which that code was written, so the functionality desired by the open spec. Then, of course, the issues all reference that, the closing comments all mention that, and the PRs also all mention that. So we have one entire line where we can always see what caused what. So what does it mean in practice? We have a doc block notation. In that doc block, we note down which specs were used to create the code that the block doc accompanies, so the method or the function. Then anytime anything changes, we add another spec. we can trace this to the specifications. Agents log any choices they make during a process to the actual issue, so we can always read back because the spec is tied to an issue. So if we have a spec, we have the issue. And anytime a bug appears, that means that we now don't just check the code, we check the system that led to the code. So do we need to change our skills? Do we need to change our ADRs? Or do we need to write specifications in a specific way? Now what this introduces is a self-learning system. So for us, any bug is value input because any bug allows us to actually improve the system and make sure that we don't create that same bug again. It's all very nice and modern, but we're still working with agents and agents can still be untrustworthy. For some reason decide to blow up your database, for instance. So what we do is we run agents within containers. And every container has limited internet access. So it may access the API that the LMM is on, it may access GitHub, and it may access Codework. That's it. Each agent has their own account, so they're always traceable. They cannot get out of the container. They don't have any destructive rights on their accounts. They may only work on their feature branches that they're assigned to from the specifications. All code gets loaded into the container at container startup, so they don't actually pull any code from GitHub or Codebug. They may only push pull requests. Every ADR gates what it's supposed to gate, so the design rule is always applied. And if anything doesn't get past the mechanical gates, then the code doesn't end up at Git. Git, I mean, it doesn't actually get merged beyond its feature branch. Because when the feature branches hit Git, so they're either on GitHub or they're on Codework, which we use these days, then all the checks get run again by workflow on the actual repository and get produced as nice results and nice reports, which then of course go back to the developer so that the developer can actually see if all checks have been applied and if the code makes sense. So, and this design principle of communicating with the reviewer through comments on the pull request doesn't just apply for the gates that are done, but it also applies for the decision-making process of all the agents. So that means that whenever the reviewer is reviewing agentic code, it isn't just reviewing the code itself, it also gets in context all decisions made by the LMMs during the creation of that code, meaning that the reviewer can actually review the entire process. And this is of course also applied if the code gets back into a loop. So if the validator decided that the code wasn't good enough and sends it back to the builder, one of those first three loops that it can do, then it also always explains why, so that the reviewer can be extra careful to see if the problems encountered were actually solved. Okay, so now we get to the fun part. Because we are using containers and images, that means that we've now seen that Hydra exists out of specifications, it consists out of ADRs, out of issues that are labeled, ready to be built. And we can now tie all this together. So we can basically write a script that looks at GitHub or Codework, sees if there are no issues that need to be built, or that are labeled to be code reviewed, or that are labeled to be verified, and then spin up a container, perform that specific labeled action, and then kill the container. That means that it's something you can run automatically. You can run it on local, you can run it on CI production environment, you can actually run it in Kubernetes if you want to, and you need to do nothing about that. The only thing that you need to do is you need to write open specs, you need to create an issue, link that to your open specs, and correctly label the issue. And that doesn't just have to be at the start. It could also be that the developer is already working on something and has a running PR and wants a code review. Then you can just label code review, then that specific container and agent will spin up, review the code, and do any adjustments that are needed. Now, it's important to know why this works. How can we make sure that this works? Well, that's because of two things. First of all, we did an immense amount of hardening. So we made the ADRs, we made the gates, we made the containers, we made the review upon review upon review. So we actually gave a very small scope for agents to work in. And that very small scope is the open spec, but we can keep that scope small because we're using frameworks. And especially here we're using Nextcloud. And that means that a lot of the work has already been done. So we're never going to ask an agent to build a user authentication flow. Or we're never going to write an open spec to do something with data storage. Why not? Because Nextcloud has already done that for us. That means that we can replicate the process which we built with Hydra, specifically for Nextcloud, and make it very portable to any open source framework. As long as the framework is open source, then there's probably enough learning on it by LMM, and then we can use agents to code additional stuff for it. So that's it. That concludes this presentation. I hope you learned something. But if you do want to learn anything more, then please be aware we have an academy, the Conduction Academy. We always post our tutorials, our walkthroughs, and any documentation we have there. There are actually 3 tutorials over there on how you can implement Hydra, and there's also a walkthrough of how you can install Hydra and get it up running locally in your environment. So if you want to know anything more about Hydra, then please look over there.